Welcome. Today's notes worksheet is entitled Factoring Polynomials. Factoring probably represents the most important and prevalent skill set that we will be utilizing this year. So let's see if we can develop a nice foundation for you as we go through this notes worksheet. I always consider factoring as really a two-step process. We're going to recognize a particular pattern, and then we're going to apply that pattern. And so we'll go ahead and see those patterns in action all through this notes worksheet and kind of break each one piece by piece. So let's start it out. At the top here I have the greatest common monomial factor. And then I guess here's what I would have you write in the blank right there. I always kind of consider this just the reverse of the distributive property. So we all know how to multiply into parentheses. This would be taking something out and creating parentheses with the remaining factor. And as it says on your paper, I kind of bolded it, I capped it, I even put an exclamation point behind it. This precedes all of the other patterns that we would look at. Always look to do this first. Then we'll see if we can recognize any of the other patterns that we investigate this throughout this notes worksheet. So always look to this to do this pattern first. So let's start it out. Example 1, I just have 3 that we'll take a look at. So letter A, I have 4x cubed minus 6x. And very simply, I have a polynomial written in standard form. And what we're going to try to do is manipulate this expression to write it as a product of its factors. And so here's what we're going to do. I have this 4x cubed. Sometimes I'll counsel students to kind of circle the 4x cubed and to circle the 6x. It's up to you if you want to do that or not. But basically, I would ask us to think about what is the greatest common factor of those two terms. What is the greatest term that divides evenly into this and into this? So we just take it in terms of the numbers first. Looks like the greatest common factor of 4 and 6 would be 2. So we're going to take out a factor of 2. The greatest common factor of x cubed in x, what divides evenly into those, I'm hoping you would agree would be x. And so as a result, the greatest common factor is going to be 2x. And so that's what I pull outside of the parentheses. And then what's left is really the remaining factor, the remaining binomial. And in this case, kind of think about it as 2 times what would give me 4, x times what would give me x cubed. And so I have that 2x squared as the first part of my binomial factor. Then here's the minus from right here, of course. And then 2 times what would give me the 6. And we've got a 3 in place right there. I've taken out this factor of x, and so I'm good to go. Again, I think you've seen that before, but really just want to kind of lay it out there. We're going to develop some more concrete terms as to how to get these values inside the parentheses, a better process, so to speak, as they get harder. But for right now, I think you can do a lot of mental math and pull it off. Okay. I would love for you to maybe pause the video or just while I'm talking about it, see if you can go ahead and take a letter B and do that successfully. So pull out the greatest common factor and then write what is left inside the parentheses. So I'm looking at the 27 and 18, and greatest common factor there would be 9. I'm looking at the x to the 5th and x to the 4th, and I'm hoping you would agree that really x to the 4th would be the greatest common factor there. And so when I pull out a 9x to the 4th, then let's think about this. 9 times what would give me the 27? Looks like I get a 3. X to the 4th times what would give me x to the 5th, and x to the 1st. And last one here, 18 divided by 9, or really 9 times what would give me the 18. Again, 2 different approaches there, but I hope you would agree that we have the 9 times 4 factors of x, and then times that 3x plus 2. And there would be the same exact expression, of course, just written as a product of its factors. Now this one's a good one right here, and I guess it kind of goes against the title of this pattern because it says, as you can see, the greatest common monomial. But watch what happens here when we try to pull out the greatest common factor. Now in this case, I actually am going to circle my 2 terms. So if you don't mind, and you can do this just very lightly. It's tough for me to do it lightly up here. But whatever, I'm going to go ahead and take a look at those 2 terms separated by the plus. And essentially, I look at both those terms, and I see that there is a common term to them. And so if you kind of look, I have an x plus 3 in this particular term, and I have a factor of x plus 3 in this particular term. And so as a result, my greatest common factor here, and I'm hoping you would agree on this, is x plus 3. It is in both of the values that I'd circled. And so as a result, I'm going to go ahead and pull that out. Now watch what happens here. And by the way, of course, this is not a monomial, this is a binomial. That's what I said, it kind of goes against the title up here, but that's all right. It is still the greatest common factor. And as a result, let's see what's left when I pull out x plus 3 from this part right here. This is gone, and I hope you would agree we have x squared. Here's my plus right in the middle. And of course, in this particular case, I pulled out the x plus 3, and so it looks like I have a 5 left. And there we go. And I guess I would ask you, if you were to multiply this back in, if you were to distribute the x plus 3 in, would you get this and would you get this? Sure. And so this is a product of two binomials, which is equivalent to this expression right here. Now, if you don't mind, try to keep this in the back of your mind here because you're going to see this on the back side of this notes worksheet. So just see how we got from here to here. So when we take a look at a different pattern on the back, when this comes up, you'll know exactly what to do with it. All right? So always, always, always look to do the greatest common factor first. See if there's anything you can pull out. Then we'll look to recognize other patterns as we go through. All right, number 2, quadratic trinomial. So quadratic is a degree 2 polynomial. Trinomial is 3 terms. That's great. This number in front here is just a 1x squared for now. Makes it nice and easy. So we'll start out with that one. I always kind of consider this one the reverse of foiling. So we've talked about foiling. So this is anti-foiling essentially, just reversing the process. And I just have a little hint as to what we're going to do here. These are relatively straightforward, but let's just fill this in and then we'll go get example 2. So what I do when kind of trying to determine what factors we're looking for, the primary piece is that we're looking for two numbers that multiply to C and add to B. Again, I know you've kind of done this before. Should be just a quick review, and then we'll go ahead and do the harder quadratic trinomials in just a minute. But that's the piece we'll be looking for, two numbers that multiply to C and add to B. And so I'll show you what this looks like as we go through. First and foremost, example 2, it does say factor each polynomial. And again, I should practice what I preach here. So in this case, what I'd be looking to do is factor out a greatest common factor. But is there anything that divides evenly into those 3 terms that would be useful to factor out? No. And so we need a different approach, a different way to factor that. And the way we factor these quadratic trinomials is by creating two binomials really, side by side. And so again, it's the reverse of foiling. So we just kind of look at it, we say, well, what times itself would give us x squared? And so x and x would do the trick. There's our first in FOIL. And then the key is going to be kind of getting the lasts taken care of in conjunction with the outside and inside. And so here's where this little trick comes in. We're just looking for two numbers that multiply to C and add to B. And so here I'm just looking for numbers that multiply to 8, add to 6, and I hope you're all right with me saying it's 4 and 2. And so that should take care of the last pieces here, the O, the I, and the L, specifically the L, and then the O and the I should take care of the middle. So let's take just a quick peek. I already told you x times x is x squared. The last, 4 times 2 is 8. That's great. And now look at the outside and inside. 2x and 4x make the 6x. And that's it. Again, would love for you to pause it. There's no reason for you to kind of listen to me go through the explanation if you can kind of pull these off on your own. So see if you can factor that one. I'll go ahead and do that momentarily. And then see if you can take care of C as well. So right away, guys, we're going to do x and x here. And again, the trick for these simple quadratic trinomials is we're looking for two numbers that multiply to negative 18 and add to positive 3. If they have to multiply to a negative, one's going to be plus, one's going to be minus. And if they have to combine to a positive, that means the greater one's going to be positive. So I'm getting a plus 6 and a minus 3, long story short there. Again, the great thing about factoring is you can always check your answer. If you FOIL this back out, of course, you should get the original. So always, there's no reason really to get these wrong unless you don't know how to do it. but you will know whether your answer is right or wrong just by multiplying it back out. Okay, this one right here, x and x, two numbers that multiply to positive 40 but combine to negative 13. Looks like probably a negative and negative in order to pull this off. So I'm thinking a minus 8 and a minus 5 would do it. And negative 8 times negative 5 is positive 40. And now you can see everybody, the outside and inside, would combine to negative 13x. Wonderful. So those were the easy quadratic trinomials. Now, everybody, we're going to look at some of the harder ones here, and what makes them harder is by throwing a little number in front of the x squared. So something other than 1 makes it a little more complex. And so same thing, I'm going to go ahead and just have you write in here that it is reverse foiling. So we're going to do our two binomials side by side, a product of those two binomials. And again, I've got a couple ways to go ahead and pull this off. I like trial and error. If you have really good number sense, I think this is a quick way to do it, and I think it's actually a more enjoyable way to do it, to be honest. I happen to have a great method to use, so you can kind of use my method. I'm not very humble about it, apparently, but I'll show you the one. I know probably about 4 or 5 different ways to kind of pull this off, and this way that I'll show you is probably as foolproof as it gets. I think so, at least. But anyway, I'll show it to you. If you like it, use it. If you know one from Algebra 1 that you like better, please, of course, use whatever works for you, not what works for me. So let's do a little trial and error and then kind of show you what we're looking for. So here we go, letter A. I make my two binomials side by side. And here's the premise behind this. Very simply, I'm looking for, my firsts have to multiply to 2x squared. So, I hope you're all right with the fact that it's probably 2x and x. I mean, there aren't really any ways I can do that other than that. And so there's my firsts taken care of. And then I want to get my lasts taken care of. And those lasts obviously have to multiply to negative 6. The problem is I have to get the outside and inside to combine to negative 1x. So I just kind of think about a couple different ways to do this in different combinations. And I might do something like this, everyone. I might do something like, plus 6 and minus 1. That multiplies to negative 6. But what I need to do is figure out if it's the right combination because the outside and inside have to combine to negative 1x. And so, I kind of do a negative 2x and a positive 6x, and unfortunately that's not even close. So outside and inside don't combine to this. So unfortunately, that's my wrong combination. Even though the firsts and lasts work, the outside and inside did not combine to that middle. So I go back to the drawing board and I say, all right, well, again, I'm pretty confident about that 2x and x. Maybe something like a 3 and 2 combination would do, something along those lines. And even before putting signs in, I'll at least get a gauge. I do have a 4x and a 3x for the outside and inside, and that has potential because 4x and 3x can combine to a negative 1x there. If I make this a negative 4x, and if I make that a positive 3x, I have my winner. And so as a result, you just kind of see a little trial and error. And again, good number sense, you can do this pretty fast, getting the lasts to match up with the outside and inside to give you that. Hope that works just in terms of a trial and error discussion. Again, what I'm going to do is just show you a way to kind of pull this off. I think it's pretty straightforward, to be honest. So here we go. Again, to me, it's always the issue of the 2. The 2 is the problem. So what I'm going to do, at least for the time being, and here would be my method in action, I'm going to go ahead and move that on over. And so here's what I mean by that. So what I'm going to do is take that 2, move it on over to the back, and 2 times 6 is going to be 12. So that's where this number comes from right here. So again, not like in the 2 out in front, what I'm going to do is combine it with the number on the back, and 2 times 6 is 12. And then what I'm going to do essentially is factor this. Now, this is easy, because this is just like the top. I'm going to factor this. I know it's x and x. And by the way, leave a little room in front if you don't mind. So x and x. And then all I'm looking for here is 2 numbers that multiply to negative 12 and combine to negative 1. So that would be a minus 4 and a plus 3. Now that's great. That's this. Unfortunately, I need to factor this. This is a different quadratic trinomial than this right here. So I'm not done. I did know that I had to get my firsts to multiply to 2x squared. But the problem is I don't know where that 2 should have gone. So what I'm going to do, everybody, is I'm going to overcompensate. I know there's supposed to be a 2 in there, but unfortunately I don't know where it is. So I'm actually going to put it in both spots. Now obviously, everyone, this is not right because 2x times 2x is not 2x squared. I put in an extra factor of 2. And so here's what I need to do. I need to eliminate the extra factor of 2 that is embedded somewhere in these two binomials. And if you look, everyone, do you see that this has an extra factor of 2? These numbers can divide by 2, and that's what I'm going to do. I'm going to divide that by 2 because I can, and then this becomes x, this becomes 2. That's where the extra factor of 2 is. The original 2 was only supposed to go in there, and it gets to stay. And look at that, everybody. There are your two factors, just like what we got up here. Kind of cool. I'm going to show you probably on one more there, maybe a couple more. We'll just see what I'm thinking at the time. I think I'm going to skip B for just the time being. I think my method would work really well on C. That's a good one to kind of talk our way through. And then, again, I think I'll ask you to pause the video and see if you can do the other two, however you want. It's up to you. Again, I like trial and error. It's quick. Again, good number sense. You can pull it off. But if you're like, just you're not as comfortable with that, then try the method. Yeah, it works. Okay, so again, I look at this quadratic trinomial. No greatest common factor. That's obviously what I would look for first. But I am going to anti-FOIL this. Again, I don't like that 15, so it goes. And so I get x squared minus 11x plus 30. That is definitely something I can deal with. And so let's go ahead and deal with it. Give me an x and x. Again, leave room in front of it. Two numbers that multiply to 30 and add to negative 11 should be minus 6 and minus 5. Okay, that's great. But again, that is not the original. If I multiplied this out, that's this thing that I just kind of modified. So I knew my firsts had to multiply to 15x squared. The problem is I don't know how to pull that off. So what I do is I put a 15 in both spots. And again, I overcompensate. I know this is wrong because obviously this is not multiplied to 15x squared. So now what I have to do is find that extra factor of 15 embedded in my two binomials. So let's take a look. If you look at this one as a factor, it looks like I do have an extra factor of 3 in here, right? 3 goes into both those. So let's get rid of the 3. 15x divided by 3, 5x. 6 divided by 3, 2. There you go. There's your nice factor right there. Now again, I had an extra 15 somewhere. Here's 3 of it. And do you see the extra factor of 5 in here? So remember I told you I put an extra 15 in. 3 of it was here and 5 of it was here. 3 times 5 would be the 15. Cool. And so let's see, 15x divided by 5 should be 3x. 5 divided by 5 is 1. And there you go. If I FOILed this out, would I get the original, which was the whole point, of course? Absolutely. Cool. Again, it would be great for you to pause the video at this stage and just see if you can factor B. I think that one's a little easier. And then D, maybe a touch harder. And then come on back, just see if you got them right. Or if not, I'll go through my method. Again, I like trial and error. I would use trial and error, but I'm just trying to give you an alternative there. Okay, so here we go. I'm going to go a little quicker now. So x squared plus 9x, 2 times 9 is 18. Let's factor it. That is something I can deal with. X and x, but leave room. Two numbers that multiply to 18 and add to 9. I'm liking 6 and 3. But the 2 has to go in. So the 2 goes in both spots because I don't know where officially it's supposed to go. So I put it in both spots, but then I've got to get rid of where it's extra. And it looks like here's the extra right here. Divide by 2, and it keeps it clean. Got x plus 3. That one was where the 2 was supposed to go, by the way, and there it is. Awesome. Letter D, here we go. 10x squared minus 17x plus 3, no greatest common factor, so I'm just going to let it ride. I'm going to do my method here. Move it on over. X squared minus 17x, add the 30, 3 times 10. This can be factored, of course. And got to be careful on this. I'm thinking a minus 15 and a minus 2. Hope that sounds decent to you. So that would be our combo there. And then the 10 is going in, but I don't know where, so I put it in both spots just temporarily. There is an extra factor of 10 somewhere in these two factors. Let's go get rid of it. So I look here, and it looks like I can divide both those by 5. So I'm thinking a 2x minus 3 after I divide both those by 5. And then here it looks like I have an extra factor of 2. So it looks like I would get 5x minus 1. And again, look, there's the extra factor of 10. Factor of 5 from here, factor of 5 from here. Get rid of them. They're gone. And now I've got these. Again, always check. It's so easy to know if you got something right. FOIL that out. If you get this, you did it correct. Okay, so those nice quadratic trinomials. Some good stuff with that. Let's move forward. All right, example 4. This one's rather quick. This is just something that we're going to see in the future in this class, and so just a couple phrases that you might hear from me. So might as well introduce it. Don't worry too much about how you express these. So it says, what do these quadratic trinomials have in common? And so if I asked you to factor this, and I'll do this rather fast, everyone, because we've got more stuff to cover on the back. If I asked you to factor this, you would say, all right, it's nice and straightforward there. It's just x plus 3 times x plus 3. And you notice, of course, that the two factors are identical, which just happens to mean that there's another way to express this algebraic expression right here. And I could write this, anything times itself is really squared, so I'm hoping you would be in agreement that that would be x plus 3 squared. So two factors of x plus 3, that's all. If you use my method on letter B, or just factored it on your own, you would see that this is 3x minus 1 times 3x minus 1. Or again, just maybe better written, and we will write it like that in the near future, as 3x minus 1 squared. All right, and then same thing here. If I asked you to factor it, the two factors happen to be the same. And so as a result, this would be x plus 1 times x plus 1, or x plus 1 squared. And so you kind of see those pieces. What they have in common, of course, is that the factors are the same. And they turn into something that I think we have seen before. We'll go ahead and name that momentarily. So let's get the polynomials in standard form, what they're called. Each of these polynomials is called a perfect square trinomial. And again, I think we've at least introduced that expression before on a previous notes worksheet. So a perfect square trinomial. This is a perfect square, this is a perfect square, and the middle term kind of fits the characteristic of factoring into this. And then let me just go ahead and shorthand this so we can move. So every perfect square trinomial factors into what is called, and we've seen this phrase as well, everybody, square of a binomial. Great name for it, of course, because that's exactly what it is, square of a binomial. I think on a previous notes worksheet, I gave you a square of a binomial, and you expanded it out, and you made it look like something along these lines. Now, obviously, the reversal is by factoring. You take that and factor it, and it turns into a square of a binomial. Again, there are going to be a lot of algebraic benefits to expressing it in this fashion right here. So if you see it, maybe a good habit to develop. Cool. Let's go. Number 4 on that back side there, difference of two squares. I think we've seen this before. Good name for this pattern, of course. Difference means subtraction. Two squares, one in front, one on the back. And again, I think we've explored this in the reverse form, but basically it transfers into what we would call the sum and difference pattern. Basically, it turns into two binomials side by side. And let's see if I can fit this in here. A plus b and a minus b. That's what it kind of fits into. And we'll go ahead and see this. Again, it's really just factoring quadratics. It's just kind of a very specific situation. So we'll go ahead and take a look at example 5 here, show you what it looks like, and we have kind of an easy, medium, hard thing going on there. So let's give it a try. So again, just its recognition and its application. I look at these two terms here, and there's no greatest common factor. Certainly always look to do that. But I see a perfect square here. 64 is a perfect square with a minus out in front. Okay, so what that means is it factors very nicely into a product of two binomials where it's just pretty straightforward. What times itself is x squared? X and x. What times itself is 64? 8 and 8. And notice, guys, this quadratic just doesn't have a middle term. Officially, there are 0 x's. How do I multiply two binomials to get together in order to get 0 x's? Well, one would be the plus and one would be the minus, and you can see the outside and inside canceling out. And so again, it's just kind of quick recognition here. Difference of two squares. Oh, x and x, 8 and 8, plus minus. Done. Okay, let's do letter B. Little harder, but recognition is good with this. That's a perfect square. That's a perfect square. Minus right in between. And so I look at this, and I get my two binomials set up, and I think about what times itself would give me that. And I'm hoping 5x and 5x sounds about right to you. And then what times itself is 36? Well, 6 and 6 would do the job there. And again, the only way that this plays out to cancel outside and inside is if one is plus and one is minus. And that looks great. Cool. Letter C is obviously not quadratic, but it is a polynomial, excuse me. It's a quartic, and it does factor, actually. Don't know if we've explored this in a ton of detail, but this obviously is a perfect square, and we'll get into that momentarily, and 16 as well. So let's start the process out. Actually, it'd be great if you can pause and see if you can factor this one completely. But if you don't want to, if you want to just kind of see it in action, that's fine as well. So again, it's just two squares with a minus in between. Let's let it ride. X squared and x squared is the only difference at this point, rather than an x and an x. So x squared times x squared is x to the 4th. 4 times 4 is definitely the 16. And again, that's great because now with a plus and a minus, the middle terms would cancel out, and that would be what I would be left with if foiling. So this piece right here. Now, one of the things I kind of really recommended was that you always look for patterns. You're always looking to go further and further and further until you can't factor any further. So I will tell you up front, this does not go any further. But I'm hoping this piques your interest a little bit. Always, as I said, recognize and apply. As a matter of fact, if you look at x squared minus 4, this is a difference of two perfect squares. So always try to catch that piece. Always look at what you have and ask yourself if you can go further and further and further. And in this case, x times x is x squared. 2 times 2 is the 4, and 1's plus, 1's minus. If you foiled this piece, would you get that? Absolutely. And so as a result, that quartic that we had was made up of a prime quadratic and two linear factors. So quadratic times linear gives me quartic. So I hope that makes pretty good sense, and just always look to go further until what you have can't be factored anymore. Now, I've alluded to it, but let's go ahead and write it down explicitly here. Difference of two squares is a great pattern, really is. But there is no sum of two squares. And I kind of said that when I looked at x squared plus 4, that actually doesn't factor. So let's write that, no sum of two squares pattern. At least in the real number system. When you start talking about imaginary numbers, you can probably pull it off. But we're really focused on the real number system at this stage, and so we're going to kind of go with this. So basically, if I was to give you something along these lines right here, x squared plus 9, I know what you're thinking. Oh, wait a minute, perfect square, perfect square. All right, but the thing is, it's a plus as opposed to a minus. What that means, everybody, is this is prime. It does not factor. And you could try a couple things. I've seen students do it. Hey, wait a minute, what about this? But if you multiply it out, unfortunately, in the real number system, you're not going to be able to pull this off. And so as a result, you can't break it down. Again, I'll let you explore that in a little detail, see if you come up with something, and please let me know. But I will tell you, there is no sum of two squares pattern in the real number system. Cool. All right, squares done. Now it gets a little more potentially obscure and a little harder. So for cubes, there are two patterns. There is now, everyone, here's the key. There is the sum pattern for two cubes. There is a difference pattern of two cubes. Okay, now we have to be very careful because we've been going back and forth with this. As it says, it's bolded for you right there. This is different than the cube of a binomial. And we've been kind of talking about working with these polynomial expressions. Just very quickly, I'll do it in terms of a plus b because that's what I have on your sheet. This is not the case. We saw this in action. So this is the cube of a binomial. And there was a pattern to expand it out, and it was actually fairly intricate and complex. Okay, now everybody, what we're going to do is look at this right here and see if we can work at this piece, but it is not equal to this. In fact, again, it's quite a bit more intricate and complex. So these two things are not the same. Want to be very, very clear about that. I've seen so many students over the years, even after kind of looking at these patterns, still want to make this this or this this. And they're not. They're just not equivalent algebraically. Okay? And we've seen it in a number of different contexts already. So here's another time to see it. Okay, guys, so here's just the approach. When we factor these cubes, difference of two cubes and a sum of two cubes, you see it breaks down into two factors. One is a linear factor, and one will be a prime quadratic factor. Same here, linear, prime quadratic. I'm going to try to get you to learn this without having to memorize all of this hoopla up here. But, hey, that is the pattern if you need it. Let's go ahead and try example 6. So, first of all, recognition. This is a perfect cube, and 8 happens to be a perfect cube. So this is definitely a difference of two cubes. So it's going to be this piece right here, and we're going to make it look like this right here. We're going to write it from standard form to factored form. One factor times a large second factor. So here's how it plays out. Let's do the linear factor first because I think that's the easiest thing to do. So you would ask yourself just what cubed would give me this right here? Well, it should be just x cubed. So we put the x right in there. It's the linear version, obviously, of this. And then what cubed would give me 8? Well, it's 2. And if that's a minus, this is a minus. This will always be the same sign as that right there. This is just the linear version of that, for lack of a better description. So x minus 2, got that. All right, now the quadratic is the hard piece, but I think we can muddle our way through at least a little bit without having to memorize this. So remember, guys, factoring and multiplication go hand in hand. So what I would say is x times something has to give me x cubed, right? So x times x squared would give me the x cubed. So I kind of know that that first spot has to be x squared. That's great. Now the last, what's going to go back here, has to kind of produce this. So the question would be negative 2 times what would give me negative 8? Negative 2 times positive 4 would give me negative 8. And so I know, again, dealing with factoring and multiplying, working in conjunction with one another, this times this is that, and this times this is that. And that's great. I've got two parts of it. Now I just need the third. And the third essentially is the linchpin here. It's what makes everything else in the multiplication process cancel out. And so there's a quick way to kind of look at it, and we go back to the linear factor. Take what's in the linear factor and take those two terms and multiply them together. X times 2, everybody, is 2x. That's what goes here. And if that's a minus, again, for everything to cancel out, that's the opposite. That's a plus. So I'll write that below, and then we'll move forward from there. So multiply terms in the linear pair together, and then I would say it's the opposite symbol. And obviously, if you're not like seeing it the first time, when we do it on B and C, hopefully it'll really click. So again, just x times 2 is 2x. If that's minus, that's plus. Now again, I would leave this up to you. We've done polynomial multiplication before. If you distributed the x in 3 times, and then distributed the negative 2 in 3 times, well, what happens is a couple things you get, this and this, but everything else cancels out. I see it kind of getting, in just my vantage point, you get a positive 2x squared and a negative 2x squared. They're gone. You get a positive 4x and you get a negative 4x. They're gone. Cool. I like that. Oh, and by the way, if you tried to factor this, you can't. So according to our traditional methods, you can't break this down just yet. We'll look at this in the future, but as of right now, you leave it as a quadratic prime. All right, here we go. Let's go get them now a little quicker. So start with the linear term right here. X cubed would give me the x cubed. 4 cubed, by the way, again, perfect cubes here. So 64 is a perfect cube, and that's good. 4 cubed would give me that. If this is a plus, that's a plus. Now play it out, everyone. X times what would give me x cubed? Has to be x squared. 4 times what on the back would give me 64? Has to be 16. So you knew that had to be a 16 right there. And then again, here's the linchpin. Let's go ahead and do it. Go back to the linear term. And you multiply these two together. X times 4 is 4x. And if that's a plus, then that has to be a minus. And there it is. Sorry, I put a little negative in there accidentally. Let's get rid of that just in case it freaks you out. There we go. Now it looks good. And there it is. Try multiplying it out, guys. You're going to get x cubed plus 64. Okay, last one here. Here we go. Now we're into a rhythm with it. Just be a little careful on this. This is a recognition of that pattern. This is a perfect cube, and 1 is a perfect cube as well. 1, of course, is a perfect square, but in this case, I think we're fitting in the cube pattern because of that. So what cubed would give me this? 2 cubed gives me the 8. X is what's cubed to give me x cubed. And then plus plus, 1 cubed gives me 1. So 2x plus 1 as the linear factor. Then let's go for it. 2 times what gives me 8? 4. X times what gives me x cubed? X squared. Cool. Back end, everybody. 1 times what gives me 1? Has to be a 1. And then get that middle term. Now it's the third time, should get it. So multiply these two things together. 1 times 2x is 2x. It was a plus originally, so now it goes minus. And there you have it. Linear times a prime quadratic. Super work. All right, again, lots of patterns to recognize, but once you do, once you see that pattern, then you go ahead and apply and should be able to pull it off. All right, last pattern that we'll see today. Let's go ahead and do it. It's called grouping. I'll just go ahead and write a few things in, and then obviously we'll go ahead and check it out with some examples. So grouping, good name for it. We're going to group the first 2 terms together. And the last 2 terms together. All right, and we'll talk about how we do that in just a moment. So group the first 2 terms together and the last 2 terms together. And then I'm just going to write it like this, and then we'll see it in action. Then very simply, treat it as a GCF problem, everyone. Greatest common factor. And I'll show you what that looks like momentarily. So we'll start out relatively straightforward. Now you can see these are some of the more complex polynomials, of course. I've got a 4-term cubic that I'm looking at initially here. That's going to be pretty interesting. And again, none of the other methods that we've seen before, none of the other patterns would apply. There is no greatest common factor at this point. And again, it just doesn't fit any of the other ones. but it will fit this grouping pattern here, and I'll tell you kind of how we can tell in just a moment. So guys, grouping. What symbols are used for grouping? Parentheses. Now, some teachers like to do this in a slightly different manner, but that first step, I like to put the first two like this, and I like to do the second two terms like that, literally kind of a side-by-side thing, kind of group them like that. Some do it in a slightly different manner. I won't tell you how, lest I confuse you. So I've got those two pieces right there, and now basically what I'm going to do is go GCF on this. I'm going to break this on down right here and think, hey, wait a minute. There happens to be a greatest common factor to these two terms that I've grouped together. And I hope you would agree, it's x squared. And so I'm going to pull out the x squared from here and here. When I pull out x squared from there, I get a factor of x left. Here's your minus. When I pull out a factor of x squared from here, I still have the 4. All right, now here's where I take a look at this, and I sort of see that there's a greatest common factor to these two. And it happens to be a positive 2. Now I'm going to include the plus with the 2 there. So that is kind of the key. Now I go ahead and use that as a positive 2. And then when I take out the 2, you see I get x, and hopefully you see it's minus 4. If it can be grouped, these two will be the same. If it can't be grouped, these two won't be the same. Okay, so as a result, now we're going to go, and by the way, this actually should look familiar. I'll be very quick on this, but we've seen exactly this piece before, if you remember how we started the lesson, and I asked you to keep an eye on it. Hang on, let me get there. Almost. There it is. Look at that, everybody. Doesn't that now look like exactly what we have in front of us? And that's what it is, guys. It's greatest common factor. That's coming out, and then we'll write it just like that. Okay, so let's go get it. Here we go. Now it's up to you. I'm not going to circle it because it's just not easy for me to do. But that term and then that term separated by the plus. Each of those two terms has a factor of x minus 4. And so the x minus 4 comes out. When the x minus 4 comes out of here, what's left, everyone? Good. And then here's my plus. When the x minus 4 comes out of here, what's left? The 2. And there you go. I would look to go further, but this is linear. This is a quadratic that can't be factored. Cool. All right, second time, maybe a touch faster, but again, good verbal explanation behind it. So let's go for it here. What factors out of these two terms? X squared. And looks like I get 3x plus 4. What factors out of these two terms? Now, be careful, especially when that's a negative. You want this to work, so you want this to be a positive 3x and a plus 4. So I'm hoping you would see that this would basically be a minus 2 coming out. And when I get this to be a minus 2, well, then that becomes a positive 3x, and this becomes a positive 4. I'm hoping you do see that piece. And if not, please let me know. So pull out the sign with the term that's appropriate. In this case, the minus. And notice they're the same. And now this just goes greatest common factor all the way through. Here's one term. Here's a second term. Each one has a 3x plus 4. And so I'm going to take the 3x plus 4 out of here and take it out of here. When I take it out of this one right here, everybody, I get x squared. Here's my minus, of course. When I take it out of here, I have the 2. All right. Cool. Letter C. Let's go for it. So it looks like I would pull out a 3x squared on that one. 3x squared. Interesting. And how about x minus 1? Here, let's pull out a positive 2, x minus 1. And I'm in the exact same position. Two terms separated by that plus right there. Each term has x minus 1 in it. Pull out the x minus 1, and I get that. All right, letter D is the great one. I know we're going a little long on this, and I'll try to round this out in the next few minutes for you. but I love letter D. See if you can really pause maybe and go all the way through. So I'm going to do it. This is as hard as it gets for us, I think, at this stage. Watch what happens here, everyone. If I look at this, I'm going to pull out an x cubed, and I get x minus 1. Now, by the way, you look at this and you're like, wait a minute, there's no greatest common factor. And you're kind of right, of course. But you do want to pull out something here, and so what you're going to probably pull out is that factor of 1 that's implied to be there. And when you do that, of course, that stays as x minus 1. So that hasn't come up yet, but for grouping, you do want to have that number there. It's implied to be there. Now you want to explicitly write it. Because when I do explicitly write it, you can see that this term right here has x minus 1. This term right here obviously has x minus 1, so it comes out. And then I have x cubed from there. And again, I did have a factor of 1 from here that's remaining. Now, here's what I would ask you. Do you think you're done? Well, I did a great job in terms of the grouping. That is correct. If I multiply this out, I'm going to get the original. No harm, did it, got it. But you're always, always, always looking to go further. X minus 1, you can't touch. But if you look at this, and here it comes, guys, is the recognition piece. That, to me, is a sum right there, of 2 perfect cubes. And so that is a pattern that we just did. So if you kind of look at it, I can break down 2 cubes with a plus in between. X and 1, and then x times x squared right there, 1 times 1 on the back, and then just following the pattern we did, everybody, 1 times x is x. That was a plus originally, and so now it's a minus. And so, not to be too much of a stickler, but yeah, you're going to see that cube come up quite a bit. So be ready to see it. That quartic, the original quartic right here, is this times this times this. Wow, wonderful. Let's keep it going on example 8. And again, if you need a breather, take a breather. But we're almost there. So it says factor each polynomial completely. And I guess what we want to do is at least initially start the process off of always, always, always look for the greatest common factor. So I look at these 2 terms, and before I consider anything, I want to see if I can pull something out. 9 and 36, guys, you're going to pull out the 9. X to the 5th and x cubed, you're going to pull out x cubed. And when you do that, you get x squared, and you get minus 4. And that is your first step. As I said, you have to be able to do that pattern first, see that one, then look at what you have and see if you can go further. I have a factor of 9, I have 3 factors of x, and I have this right here. And the hope is that the light goes on for you right there when you see that, because that is one of the patterns that we looked at today. It is what is called a difference of 2 squares. And so it turns into x plus 2, x minus 2. That's factored completely. All right, so go GCF and then go further if you can. Same thing here. 8, 14, and 30 does have a GCF numerically there. I'm thinking the 2 wants to come out. And then I've got a 4x squared minus 7x minus 15. So the factor of 2 is just kind of hanging out there. That'll be fine. But this quadratic trinomial we should kind of pursue a little bit. I would ask you, see if you could factor this yourself. I'm going to show you my method one more time because now I've taken out the greatest common factor. I'll show you my method on this just for the time being. That goes over. And so I get x squared minus 7x minus 60. And what we need here is our 2 factors. Let's see how we want to play this out. So I need 2 numbers that multiply to negative 60 and add to negative 7. Just to move this along, guys, I'm going to give you the minus 12 and the plus 5. Remember, the 4 goes back in. And I'm going to go ahead and draw this as that's got to come down. Remember, I did put an extra 4 in according to my pattern there. In this case, there's the extra 4 because now it divides. This was fine. That's where the 4 should have gone. And again, I did have a factor of 2, interestingly enough, from the beginning. So there's that factor of 2, and there you go. All right, guys, that was a lengthy, lengthy lesson. Holy. But again, look it over. Take your time with this one and make sure you really can see these patterns and then apply them as they approach. All right, please let me know if anything comes up here in terms of these patterns and recognizing them. And practice, practice, practice on this. We'll be factoring a lot over the course of the year. Thanks for listening, guys, of course.